So, but before that, every statement here today, there is a much simpler or more intuitive proof to get. So for instance, how do we get 1 plus 2 plus 3 up to n? How do we get this formula? So one idea is this is actually something that is observed by Gauss when he was in the primary school. So Gauss in the primary school, there is a famous story. The teacher wants the student to be occupied so that he can take a rest. So he asks the student to do what? You add everything from 1 up to 100. And then before that, you don't talk, you just work out, okay? But then after a few minutes, or maybe even faster, little Gauss replied the answer, so it is 5050. And then the teacher didn't know the answer, but after that, after doing this tedious addition, finds out that it is correct. He thought Gauss is actually cheating. But what Gauss did is so he observed that if you have a sequence of 1 plus 3 plus anything up to n, then you can what? You can repeat this, you can write down this one in the backward order. So that this is becoming n plus n minus 1 plus things up to 1. Is that okay? So we will have now two sequences of the same value, and then try to add them up. Now to add them up, this time suddenly becomes easy. You add it by vertical first, so we will have n plus 1 for the first term, and then you will also have n plus 1 for the second term, and so on and so forth up to the last term, it is also n plus 1, right? Right? So that means that, so this is actually equal to that n terms is equal to n plus 1. Is it okay? Now, if this is the value that you want to compute, let's say call this x, then this will be exactly equal to 2x. So x will be n times n plus 1 over 2. Okay, so this is how Gauss can compute 1 up to 100. So 1 plus 2 plus 3 up to 100. If you do this in the opposite way, so each term will be 101. Is that okay? And there are 100 terms. So you multiply this by 100 and divide it by 2, so you get 5050. Is that okay? Good. Okay. So this is how we can quickly compute this one. And how about this one? How about 1 plus 3 plus 5? This one is also easy. If you look at this, so you have one thing here, and then you try to add 3 things here, then you form a square. And then if you want to further add 5, then you get 9. Is that okay? And then further, the next one that you are going to add to make it a square will be exactly 7. Okay? So that's why if you have the next integer, next odd number added, then you make the square larger and larger and larger by layer by layer. So you get this one is equal to n squared. Is that okay? Now, how about this one? This one, I've seen a proof that is very nice yesterday from Facebook. So how do we do this? Okay. So let's do 1 square. So we have 1, 1, and then I have 2, 2, and then I have 3, 3, and then I have 4, 4. Is that okay? Let's say we do 1, 2, 3, 4, 5. Then I have 5, 5, 5, 5, 5. Is that okay? Is that okay? Now what I'm going to do, so this is one thing. So I'm going to, this looks like a equilateral triangle, right? So I rotate it by 120 degrees. So what will happen? So I will have, so I will have what? So I will have 5, 5, 5, 5, 5, and then I have 4, 4, 4, 4. I have 3, 3, 3. I will have 2, 2. I will have 1. So this is by rotating this by 120 degrees like that. Is that okay? Okay. And then let's rotate it one more time. rotate it one more time. Then I will have what, 5, 5, 5, 5, 5 here. And then I will have 4, 4, 4, 4 here. I will have 3, 3, 3 here. I will have 2, 2 here, and I will have 1 here. Is that okay? So far, so good. Okay. Now, summing all the values inside a triangle is equal to 1 square plus 2 square plus 3 square up to 5 square. Is that okay? Okay. So if I sum everything on this triangle, sum everything on this triangle, and sum everything on this triangle, it will be equal to 3 times the answer that we want to compute. Okay? Now, if we sum everything, then what will happen? So we have 1, 5, 5, you add up to 11. This entry is 2, 5, 4, you add up to 11. 11. You have 11 everywhere. You actually have 11 everywhere. Is that okay? Reason. There's nothing special. This one is n. If this is 1, 2, 3 up to n, this one is n, this one is n. So we get 2n plus 1. This one is from n to n minus 1. This one is from n minus 1 to 1 to n. So if you add them together, so this will be, so the previous one is 2n plus 1. So the previous one, if you add these two, it is 2n. Then this one, if you add these two, it will be 2n minus 1. But then you are going to add 2 back. So in that case, you resume the total sum will be 2n plus 1. Is that okay? So here, this is like from n minus 1 to n minus 2, n minus 2, n minus 1, n. So if you add things together, each corresponding 2 times adds up to n minus 2. But then you have a complement here, 3. So if you add things together, you will get 2n plus 1. Is that okay? So that's why everything adds up to. So this one is actually, in general, it is actually 2n plus 1. Is that okay? Is that okay? So what is the total sum of values here? Then this will be very simple. In general, this will be equal to, every term is 2n plus 1, right? You have how many terms? 1 plus 2 plus 3 plus 4 up to n. So we have done that before. 1 plus 2 plus 3 up to n. It is equal to n times n plus 1 divided by 2. Is that okay? You have these many terms, and then this will be equal to 3 times the value of 1 square plus 2 square plus n square. Is that okay? So we get the same result. N times n plus 1 times 2n plus 1 divided by 6. Is that okay? Okay. So all these proofs are very nice. Okay. Okay. Yeah, I hope you like it. Okay. Okay. So the induction that we have, the induction principle that we have just did is we have this as the basis case. Is about P1. Is that okay? And then we have the inductive case. So for inductive case, we will have Pk implies Pk plus 1. Is that okay? So the conclusion here will be, then we have, suppose that this is true and this is true, then we have what? Pn is true for every n is equal to 1, 2, 3, up to infinity. Is that okay? Now, for one thing, we can actually change the base case. It need not be 1. If it is also working for 0, then we can have P0 here. If we have P0 here and we have this one, then we can extend this to for every n is equal to 0, 1, 2, 3, up to infinity. Is that okay? And similarly, we may have the basis case, we started from 5. Then in that case, then we will have for every n is equal to 1, not 1, 2, 3, but this time 5, 6, 7, 8, then it's going to be true. Is that okay? Okay. So this is a minor variation. But there is another type of induction. So let's say the basis case is also like this. So let's say this time the basis case is P1. And this time the inductive case is slightly more complicated. Let's say the inductive case is you have P1 and P2 and so you have this one implies Pk plus 1. Okay. So inductive case is you assume that P1 is true, P2 is true, up to Pk is true. And then you show that if this is the assumption, we will have Pk plus 1 to be true. Then, again, we will still be able to show that Pn is true for every n is equal to 1, 2, 3. Okay? What is the reason? The reason is that if we have shown these two, then what do we have? We will have P1 okay, right? And then if you have this one, then we will have P1 implies P2. So that we will have P2, which is also okay. Okay? And then if you look at this, then we will have something like P1 and P2 implies P3. Because we now have P1, we now have P2. P1 and P2 will be true. And this is going to be true, then what does it mean? It implies that P3 has to be true. Is that okay? And similarly, we will then have P1 and P2 and P3 implies P4. So we will look at this P1, P2, P3 that we know they are true, so that we know P4 is true. Is that okay? Is that okay? So this also works. Usually, we have a name for this one. This is called the weak induction. And this one is, we usually call it the strong induction. So, which one is better? Is weak induction better or is strong induction better? Which one can prove more things to be correct? What do you think? Okay, I'm tricking you. Actually, the power of weak induction and the power of strong induction are the same. So if something can be proven by weak induction, it can always be proven by strong induction, and vice versa. Similar. So that means that if anything that can be proven by strong induction, you can also have something, a different proof, that just use weak induction only. Okay? But then for us, we are not talking about theoretical, which one is stronger, which one is weaker. But as a user of this induction technique, then it is much better to use strong induction. The reason is that in the end, we want to assume something to be true and then prove Pk plus 1, right? Now, this one we can assume a lot of things. That one we just assume Pk. So if you can assume more things, then you will have more things to base on. You have more ways to simplify things, right? So in that case, our proof will usually be shorter. Okay? And then, indeed, so a lot of proofs, it is shorter or it is much easier if we use strong induction. So let's see. So for instance, suppose that I have a function that I want to write a program to generate the Fibonacci number. Okay, so say I don't know how to write, somehow I don't know how to write a for loop, but I know how to write a recursion. Okay, so let's say Fibonacci number, let's say f1 is equal to 1. Sometimes people, okay, and f2 is also equal to 1. Yeah, it depends. Sometimes people say f0 and f1, they are 1. Yeah, but for this example, let's say f1 is 1, f2 is 1. And then for fn, in general, this will be equal to fm minus 1 plus fn minus 2. So this is for n is greater than or equal to 3. Okay? So let's write the recursion for this one. So someone writes this as a recursion. So it writes down integer f. So we have an integer n somehow. So I'm using C, okay. So if n is less than 0, then we will report some error, return whatever. So let's say we are not going to compute anything that is like f minus 1 or f0, less than or equal to 0, okay? Okay, then if n is equal to 1 or n is equal to 2, then I will just return 1. Is that okay? If it is not these two cases, so we will not go across this return statement, then I will just return f of n minus 1 plus f of n minus 2. Okay? So I'm going to write a program like this. Okay? Now the question is, after I write this program, I want to make sure that this program is correct. So how can we do that? Of course, you can compile it and run. Okay, you have a main function and do a couple of Fibonacci values. Okay, it works, then it works. Okay? But to make sure that it is correct, then it is actually very simple. We are going to use induction to show that it is correct. So the induction argument is going to be, so we are going to show that our program is going to be correct for n is equal to 1, 2, 3, up to infinity, let's say. Let's forget about whether there are overflow problem. Let's say we never overflow. So it is going to be correct for n is equal to 1, 2, 3, up to infinity. Okay, how do we show? Okay, so first of all, we have something as the basis case. So let's try to have these two as the basis case. It doesn't matter, we can have a lot of basis case. Okay, you can have 1, 2, 3, up to 10 as the basis case, that's okay. Okay, the problem is whether you can further use constant number of statements to show that the remaining cases are also correct. Okay, so this program will be correct when n is equal to 1, right? Right? Yeah, because when n is equal to 1, then it will go into this line, and then it will return 1. So it is correct. Okay? And then this program is also correct when n is equal to 2. Am I correct? Yeah, because when you plug in n is equal to 2, then you go into this line, and then it will return 1. Is that okay? Now the next thing that is most amazing is what we are going to assume. Assume that this program is correct when n is equal to 1, 2, 3, up to k. So we want to show what happens when we are getting the value of k plus 1 instead. So if I get the value of k plus 1 instead, and then k plus 1, let's say this time it is not 1, it is not 2, then you will go into this line. Am I correct? And then you will find out, okay, what is the value of fk? And then you will find out what is the value of fk minus 1. Is that okay? But then the induction assumption tells us that the program will be correct to compute fk. And the program will be correct to compute fk minus 1. This is by the induction hypothesis. So we will get the correct fk, we will get the correct fk minus 1. So in the end, we will get the correct sum, fk plus fk minus 1. And this is the value of fk plus 1. That is what we need. So we have just shown that when we have k plus 1 inside here, then we will still be able to compute things correctly. Is that okay? Okay? So we are not just assuming that fk is correct. We are assuming that not just fk, but also fk minus 1, it is also correct. So here, this is the flavor of strong induction. We have more things to assume. Then we can have an easier life to show that pk plus 1 will be correct. Okay? And then the statement won't be longer, won't be much longer. Instead of assuming that pk is true, you write down assuming that p1, p2 up to pk is true. You just replace that thing with this one, and then you are using strong induction instead. Okay? Okay? Okay. Okay, let me tell you, so far we are looking at things that mathematical induction works. But let me tell you one thing before we break. So something for you to think about it. So I'm going to prove a wrong thing. And then I hope that you can find out what's wrong with this proof. So I'm going to show that in a group of n, let's say n is greater than or equal to 1 cats, all cats are of the same color. Okay, now this cannot be true. I'm saying that in any group of n cats, then all of them are of the same color. You can see that, okay, in this life, real life that we have, there is white cat, there is black cat, there is brown cat, right? So if I get a white cat and a black cat together, then we have 2 cats and they are not of the same color. So this is something that is wrong. But I'm going to use mathematical induction to show that it is correct. What does that mean? That means that my usage of mathematical induction has problem. And then you need to find out what's wrong with that. Okay? So this is my proof. So this is my proof. So I make a question mark here. This is a wrong proof going to be. So basis case is correct. Which says in, so basis case talks about, okay, for instance, let me write down, try to use fewer, write down as few things as possible. So first of all, let Pn denote the above statement. So if it is denoting this above statement, so we will have the basis case as P1, n is equal to 1. And in a group of 1 cat, all cats are of the same color. So 1 cat, it must be of the same color. Nothing to argue, so P1 is true. Is that okay? Then assume Pk is true. So assume Pk is true, what does that mean? So in a group of, if there are just k cats, implies all same color. This is what we are assuming, right? Okay, and then the next step is we want to show what happens when we are considering k plus 1 cats instead. Okay. Then when we have k plus 1 cats, we have k plus 1 cats, we will take out a cat x. Say, let's call it x. So we take out a cat. So we have k plus 1 cat. We take out x. We take out x. Is that okay? So what does that mean? So there are going to be k cats here. Is that okay? We take out x. So this will implies what? Implies that we take out x already, and then here they are same color, right? Is that okay? And then what do we do next? What do we do next? Next, then take out, so we are going to put x back and take out another cat y. Then we put x back. And take out another one, another cat. Let's call it y. Okay, so what we are going to do, so we now have this one. So x goes back, but we take out y. Is that okay? Is that okay? And that means that what? There are now k cats again. Take out x, put back y. There are k cats again. And then this implies what? This implies, by induction, this implies so y is now here, x is now back, and then they are of same color. Okay, is that okay? Now x has the same color of the cats here, and we will just put y back. So y is inside here. Y will have the same color as the cats there. So x and y will have the same color. Then in that case, x, y, and all the cats here will have the same color. So all the k plus 1 cats will have the same color. So we have finished the inductive case. So we have P1 true. We have PK. PK implies PK plus 1. So that means that, okay, in a group of any n cats, all of the cats will be of the same color. Okay, find out the mistake. So let's take a 15-minute break. Please come back at something like 3:25. Okay.